Good morning, students. In the previous lecture, we study the impulse response and the step response of simple RC circuit. Today, we will see in more detail. We will see how we find the impulse response and the step response and the frequency response. We consider a simple RC circuit with a resistor and capacitor in series, and we'll have an input source voltage Vs of t, and we'll find the capacitor voltage. We'll determine the unit step response of the system, which we denote here as S of t, and we'll determine the impulse response of the system, denoted as h of t, and we'll determine the frequency response h j omega. And we will plot the impulse and the step response, for example, for R1 ohm and C1 farad. We'll plot both the magnitude and the phase part of the frequency response. Okay, this is the RC circuit. This is a voltage source, and we have a resistor and we have a capacitor in series. So a current IT flows, the same current flows through the resistor and the capacitor. So we'll find the relation between Vc of t and Vs of t. And we assume an initial capacitor voltage which is equal to 0 for this problem. Now, let the input voltage is again denoted as x of t is equal to Vs of t, and the output capacitor voltage is y of t is equal to Vct. Using KVL, applying KVL in this loop, we have minus Vs of t plus Vr of t plus Vc of t is equal to 0. So, which means Vs of t, the source voltage, equals Vr of t plus Vc of t. But Vr is R times I of t, the current I of t. The current I of t is given by C times the derivative of the capacitor voltage Vc of t. So we substitute for I of t here, and we get Vr is equal to R times C dVc by dt. So Vs of t equals Rc dVc by dt plus Vc of t. Now look here, what is Vs of t? X of t, our input, and what is Vc of t? Y of t, our output. So if we see the relation between the input x of t and the output y of t, they are related through a differential equation, first order differential equation, of course, because we have only the first derivative of y. So from chapter 2, we can have the A case here and the B case. The A case, the coefficient for y, and the B case, the coefficient for x of t. Here A0 is 1 because the coefficient of y is 1. A0 is the coefficient of y. A1 is R times C, the coefficient of the derivative of y. B0 is 1, the coefficient of x of t. N is equal to 1, first order, because we have maximum derivative for the output y, first derivative. M equal to 0 because no derivative for x of t. So first order differential equation. Now we found the A case, we found the B case. What's the next step? We can find the unit step response of the system. That means when we apply unit step input, a voltage of 1 volt starting from t is equal to 0, what will be the capacitor voltage Vc of t? So we use the method of chapter 2 again. We'll find the homogeneous solution and the particular solution. Okay, the homogeneous solution is given by, and then the complete solution. The homogeneous solution is given by summation from 1 to n ci e to the power of rit, because we have first order n is equal to 1. So ci e raised to rit means c1 e to the power of r1t. So we have one root, so we will have c1 e to the power of r1t. If it is second order, we will have c1 e to the power of r1t plus c2 e to the power of r2t. But for this case, because we have first order, we will have only c1 e to the power of r1t. Now, how we find R1? We find R1 from the characteristics equation, or we call it the polynomial equation. The polynomial equation is given by from k0 to n ak, r power of k is equal to 0. From k0 to 1 ak, r power of k is equal to 0. a0, r power of 0 plus a1 times r is equal to 0. So a0 is 1, a1 is rc, times r is equal to 0, which means rc times small r is equal to negative 1, or the root r1 is equal to negative 1 over rc. Therefore, the homogeneous solution becomes c1 e to the power of negative 1 over rc times t. Now we found the homogeneous. The next step will be the particular solution. Please keep in mind we have a unit step input. Then the particular solution will be similar to the input. So it will be Cp times Ut. So we need to find the constant Cp. Where we find the constant Cp, we'll find it from the differential equation. Differential equation is x of t is equal to Rc yp of t by dt plus ypt. Now we need to find the derivative of yp, for t greater than 0. For t greater than 0, yp is equal to cp. Then the derivative of cp is equal to 0. So the derivative part is 0. That means the input is x of t is ut. So this part is 0. So ut equals to cp times ut, which is cp is equal to 1. Therefore, the particular solution is equal to ut. Next step is a complete solution. What is a complete solution? Y of t, yh of t plus yp of t, c1 e to the power of minus 1 over rc times t plus ut. Now, is this solution complete? No. Still, we need to find c1. Where do we find c1? From the initial condition. Vc at 0, which is equal to y at 0, is equal to 0, which means y at t is equal to c1 e raised to minus t over rc plus 1. Then at t equal to 0, c1 plus 1 is equal to 0, and c1 is equal to minus 1. Then the final solution becomes y of t 1 minus e to the power of minus t over rc, everything multiplied by ut. What is this? This is the step response of the system. That means the output of the system when the input is a unit step function. So how we find the impulse response? Easy. We find the impulse response from step response. So the impulse response is the derivative of the step response, the derivative of 1 minus e raised to minus t over rc for t greater than 0. The derivative of a constant number 1 is 0. The derivative of the second part is negative 1. We have negative 1 here. The derivative of the exponential part is negative 1 over rc e to the power of minus t over rc. Then we find 1 over rc e raised to minus t over rc, which is the impulse response of the system. So h of t is 1 over rc e to the power of minus t over rc ut, which we saw it in the previous lecture. Now, next, how do we find the frequency response? The frequency response is simply changing the impulse response from time domain to frequency domain using Fourier transform. So h omega is from minus infinity to infinity h of t e to the power of j omega t dt. Then substitute for h of t 1 over rc e raised to minus t over rc times ut times e raised to j omega t dt. Then because of u of t, we integrate from 0 to infinity. and we add the exponent part here, and when we add, we have 1 over RC plus j omega. Then we integrate this. We use the rule of integration for exponential function. It will be negative 1 over RC j omega from infinity to 0. So from infinity to 0, at infinity we have e raised to minus infinity, which is 0, 0 minus 1, negative 1. And when RC goes here after simplification, we have h j omega 1 over 1 plus j omega RC. What is this? This is the frequency response of the system. That means changing the time domain impulse response to frequency domain. We can write the frequency response in terms of polar form. This is rectangular. In terms of polar, so the numerator is 1. So in terms of polar, it stays 1. And then the denominator is, in terms of magnitude, 1 plus omega RC square, plus in terms of phase, e to the power j tan inverse of the imaginary omega RC over the real part, which is given by this. Then when it go up, the positive will become negative. So this is the polar form of the frequency response. This is the magnitude. This part, we call it the magnitude of the frequency response. And this part, minus tan inverse of omega RC, is the phase of the frequency response. Okay, so for R1 ohm and C1 farad, the step response, we just substitute R equal to 1, C equal to 1 farad. These are standard units. And then the step will become 1 minus e raised to minus t times ut. And the impulse response, e raised to minus t times ut. And tau is called the time constant. At tau is equal to RC, we have the capacitor voltage approximately 0.63 or 63% of the input, because the amplitude of the input is 1. So it is 63% of 1 is 0.63. So it reaches 63%. And this time constant tau determines how fast is the capacitor is charged, how quickly the capacitor is charged. If tau is small, then the capacitor is quickly charged to the steady state value. And if tau is big, it stays longer. And the impulse response is, of course, a decaying exponential function given by this graph. Next, we plot the magnitude and the phasor response as a function of omega. So here, the magnitude is the absolute value, which is 1 over square root of 1 omega RC square. Just substitute. We can substitute R and C. Or also, we have a frequency of interest. The frequency omega is equal to 1 over RC is called the cutoff frequency in radian per second. At omega equals to RC, we have omega equals 1 over RC. When we substitute, we get the magnitude is 1 over radical 2. At omega 0, the magnitude is 1. So the value at omega 1 over RC is equal to 1 over a square root of 2 times the value at omega equals to 0. That's why it is called cutoff frequency. So at omega, negative 1 over RC, same, it will be 1 over radical 2. And at omega 1 over RC, what is the angle, the phase? 1 over RC, tan inverse of 1 is 45 degree, because I have minus 45. And at omega, negative 1 over RC is positive 45, which is pi over 4. At omega 0, it is 1. At omega infinity, the magnitude is 0, because 1 over infinity is 0. And at omega minus infinity also the magnitude is 0. At omega infinity, the angle tan inverse of positive infinity is 90, because I have minus 90, which is minus pi over 2. And this is the plot of the frequency response as a function of omega. You see at omega 0 it is 1, at omega 1 over RC 1 over radical 2. 1 over RC is called the cutoff frequency in radians. This is a low pass filter because the response has high gain at around 0 and very low gain and at high frequencies and close to 0 when the frequency becomes very high. Okay, and here is the phase as a function of omega. At omega 0 it is 0, at omega 1 over RC pi over 4 minus pi over 4, and at omega negative 1 over C pi over 4, and at omega infinity minus pi over 2, and at omega minus infinity is pi over 2. As I said, at frequency 0, the magnitude square is 1. At frequency 1 over RC, the magnitude is 1 over radical 2, and the magnitude square is 1 over 2. So if we write it in decibel means tail log of the magnitude square, tail log of the magnitude square, tail log of 1 is 0 dB. At omega 1 over RC, tail log of 1 over 2 is minus tail log of 2 minus 3 dB. So the value at omega 1 over RC is 3 dB below the value at omega 0 dB. So we call this minus 3 dB frequency or cutoff frequency. So the cutoff frequency is 1 over RC. In terms of F, it will be 1 over 2 pi RC. Okay, so cutoff frequency of simple low pass filter is 1 over RC in radian per second. And in terms of Hertz, omega C over 2 pi, 1 over 2 pi RC. I hope you understand a simple low pass RC low pass filter and how we derived the frequency response, the impulse response, and the step response. If you have questions, you can email me, you can always email me. Thank you for listening to this lecture.